Now that we've learned how to identify how many sig figs a given number has, what we want to do is we want to talk about how to know how many sig figs all the numbers in an actual lab report should have. So if you measure a quantity, how many sig figs should it have? And if you calculate a quantity in a lab report, how do you know how many sig figs that should have? The first rule you should know is that the precision or decimal place of any number you write on a lab should also match the precision or the decimal place of its corresponding uncertainty. For example, here are some incorrect examples listed incorrectly. This number is listed to the hundredths place, while the uncertainty is only at the tenths place. That's inappropriate. Same with this. This is at the ones, where this is at the tenths. And this one is even inappropriate, even though it looks like it's listed out to the ones place. Since there's no decimal point here, these two zeros are not significant, and that means this is the last significant value, which means that this number is technically only listed to the hundreds place, while the uncertainty is at the ones place. Now these are the correct versions of all these, or could be correct versions. You can see here it was rounded, the number was rounded to match the uncertainty. You can see in this one the uncertainty was rounded up to match the number, and in this one again we rounded the number to match the uncertainty by just putting a decimal place there. Now it's listed. Now you can't just arbitrarily change one or the other. It matters which one you change. I just, for example, arbitrarily changed one so that they'd be listed correctly. But there is a method that you must follow to know which one you have to round. Whether you round the number to match the uncertainty, like in this case, you round the number to match the uncertainty, or you round the uncertainty to match the number. And we're going to teach you how to know which one to do. Which method to do depends on whether your number was actually a measured quantity or a calculated quantity. If you measure a quantity, for example, you use your timer and you time how much time something takes, and let's say you measured 2.34 seconds, and you feel you are 0.3 uncertain. Now, how did we come up with that number? If it's an estimated guess based on the instrument we used and the method we used that instrument. If you want to learn more, go watch the video about knowing the uncertainty of a measured number. So let's say this is its uncertainty that we've determined. This is incorrectly listed, what would be the correct way to list it? Well, the general rule that you should always remember with measured numbers is that the uncertainty is king. What I mean by that, and that's a phrase I'll frequently use, what I mean by that is that with measured numbers, if the uncertainty is king, you've got to match the number to the uncertainty. Okay, so we're going to correctly round this value to this. Now the reason why the uncertainty is king is because if you are unsure about the tenths place of a number, what right do you have to list it to the hundredths place, right? If you don't even know what this number is, if this number could go up or down by 3, why are you even bothering to tell me what this value is here? Okay, so we always match the number to the uncertainty for a measured number. This one down here, we can see that the number was measured here. If we measured a distance of 2 meters and 35 centimeters, but our uncertainty is 6 millimeters or 0.006 meters, right? We've got to match. We can even, uncertainty is king, right? We've got to match the number to the uncertainty. We can even take this and we can make it more precise. Usually this happens, doesn't happen as often as this first case, but usually this happens because someone didn't bother to actually write down the millimeters. Even though they actually measured 235, they actually probably measured 235 exactly and no millimeters, right? I bet you can use a ruler to measure that it's 2 meters, 35 centimeters, and no millimeters, right? With pretty good accuracy. And so your uncertainty should be in the millimeters. And this person probably just wrote out this value and then just forgot to put their 0. That 0 should be there so it actually matches the uncertainty. How many significant figures a calculated quantity has, however, is a little bit more complicated and is solely based off of the operation you use to actually get that calculated quantity. There's a rule for sum and difference, product and quotient, nth power, nth root, and average. We're going to discuss each one of these. Let's look at addition. If we wanted to find the total mass, we had two objects that we massed, and we needed to find the total mass together. Okay, and we wanted to add these two numbers. This number is listed to the tenths place, the hundredths place is unknown. This number is listed to all the way out to the hundredths place. You add the two numbers and you'll get this value right here. But how should we round it in order to have it to be the correct number of significant figures? Well, let's see here. A known number in the tenths place, 2, plus a known number in the tenths place, 4, is going to be 6. And that should be known. That makes sense. However, a known number in the hundredths place of 5, plus something totally unknown, is going to be something totally unknown. You have no idea what this number is going to be. It is inappropriate to list this number. So we need to round it up to the tenths place, so the actual number should be reported as 38.7. Now, what this means is we have a rule here that we're going to use, and we're going to use this rule each time. This means that the resulting number, the final calculated number that you should have, should be listed with the same decimal place as the measured number that has the smallest decimal place. So we measured this value, we measured that value. He's listed to the tenths, he's listed to the hundredths. This guy has the smallest precision, or the smallest decimal place. So tenths place. So we're going to list the final number also to the tenths place. Here's another example, except with subtraction. We do the same thing, right? So this one's listed to the tenths, this one's listed to the ones. Oh, actually, this one's listed to the tens place, while this one's listed to the tenths place. There's no decimal point here, so that means this is not significant, right? So it's the tens place. The actual calculated number is 32.7. We got to round it all the way up to the tens right here. So the actual number should be reported as 30. Now, a lot of people have issues with this. They don't like how much they had to round this, and that bothers them. Well, the real truth is, if you don't know what this number is, you have no right to report this number over here. Okay? 2 plus some unknown number is something unknown. That's why we're going to have to round it. So a decimal point there, if you actually meant 10 exactly, you got to put a decimal point there. Then that makes that value significant. Now, the rule for a product and quotient is very different than that of sum and difference. The reason is because you're not taking a known value, like the tenths place, and adding it to the tenths, and an unknown, and adding it to a known, therefore making the hundredths unknown. Instead, what you're doing is you're taking known values and you're multiplying it by each one of these known values. So everything should, in a way, be known-ish. But the problem is that the ending result usually has a lot more numbers than either of the starting two, right? So this is like saying we're so much more precise than we actually were. Here we only had 2 digits of precision, or in other words, 2 numbers of significance, while here we had 3 numbers of significance. And here now all of a sudden we're saying, wow, look at how much significance this number has and how precise we really were, when we weren't. So what we're going to do instead is we're going to say, well, if this only has 2 numbers of significance and this has 3, let's stick with the number with the least amount of significance, and we'll make the final amount match it. So we'll round it to 14 meters is the distance, and we'll say, okay, so that has 2 sig figs and it'll match the one with the smallest. So the rule in general is, and this is also found on your pink sheet, the result should have as many significant figures as the measured number with the smallest number of significant figures. Okay, so let's look at another example, except this time with division. So if you want, pause the video and see if you can figure this one out for yourself. Okay, if you did it, the answer should be 3,000. If you thought the answer was 2,590, well, that's probably because you were thinking this had 3 significant figures. Remember, there's no decimal point. This only has 1 significant figure. I don't know these numbers. They're just placeholders. If I put a dot there, then I know them. Okay, this isn't exact. So therefore, 1 sig fig, this should have 1 sig fig. That's rounded quite a bit. The rule for nth power and nth root is very similar to that of product and quotient, as they are very similar in process to them as well, of how you actually find the nth power. So the actual rule says that the result should have as many significant figures as the original measured number. Since there's only 1 original measured number, you're just going to match this significance. So if 2.3 cubed, if we're trying to find the volume of a cube, 2.3 cubed is 12.167. You're welcome to pause it and see if you can get it right. How many sig figs should it have? And try it for the other one. The answer should be 12 is the answer, right? So with only 2 sig figs, because this only has 2 sig figs. And down here, the answer should be this big number, and the reason is because this has 1, 2, 3, 4, 5, 5, 6, and there's a dot there, right, your decimal point. So this is 6 significant figures, therefore your answer should have 6 significant figures as well. Average is always a little goofy because really what you're doing is you're adding and then you're dividing. But we're just going to say in general, when you average, the result should have as many significant figures as the original measured number with the smallest number of significant figures. So if these all have, or this has 3, that has 2, if this has 4, 3, 3, 2, this final answer should have 2 as well. One of the biggest problems we have with making sure all the numbers are listed to the right significance, or has the right number of sig figs, is that some numbers have hidden significance, and it's because some numbers are exact. For example, if we need to find out what 3 times this mass right here is, 21.1 grams, and I need to find 3 times that, right? The actual calculated quantity, or what my calculator would spit out, is 63.3. So how should I round this? Well, you would normally think it would be 60, because this has only 1 sig fig, and so therefore this should only have 1 sig fig too. But the problem is this is not just 3, but this is exactly 3. This is 3.0000000, an infinite number of zeros. So exact numbers have an infinite amount of significance because you know it's exact. You don't want to multiply. It's not a measured number where you're not sure. You know it's exactly 3. You have to exactly triple this mass. So therefore, the number with the smallest significance is this number here. So the actual number should be listed as the actual calculated quantity with 3 sig figs, 63.3. Here's another example. A lot of times pops up. If you're finding the reciprocal of a number, so 1 divided by that number, okay, it should have, again, 1 is exactly 1. This is 1.000, even though we never write it that way, because we don't want to, if we'd be writing zeros forever. So that means that this has the least number of sig figs. It should have 1, 2, 3 sig figs in the end. The 0, there's no point. The 0 is not significant. So the final answer has 3 sig figs. And again, one more common example, right, in a lot of formulas where there's a number already in the formula, like 2, when you're trying to find the circumference, it's an exact number, but also some numbers that we know very, very well, like pi. Your calculator, when you punch in pi, it actually knows a lot of those digits, so it has a very good, or a lot of numbers of significance. So again, you're going to stick with this guy here and his least amount of significance, because this is exact, and this, though it isn't exact, has a lot of significance. Okay, and the last thing we need to cover is about how to handle multiple calculations. So when you're doing something like, you're trying to find velocity, and so you have to find displacement by finding the change of position. So maybe this is the final, this is the initial position, divided by the amount of time it took. You're trying to find its velocity. You'll get your velocity here, but this is multiple calculations, right? How do you find the ending significant values for this? The thing you want to do is make sure, number one, you do not round your numbers at all until you get to the very final calculation. So don't round anything and get to your very final calculation first. Then you want to round it to the correct number of sig figs. And how you figure out how many sig figs is that then you got to do the calculation again, but this time doing it step by step. So let's do this first one together, the first top part. So this minus that is 0.417. How many sig figs should this number on top have? Well, we're subtracting, so we have the least amount of place, not significant figures. So this is listed to the hundredths place, thousandths, so we're going to go with hundredths. So we got to round it to this digit right here. So this becomes 0.42 over 0.362. And then my final calculation then, when I divide this out, we already know that value should be this. But how many sig figs should this have, right? So, well, this now has 2 on top. This has 3 on bottom. I should stick with 2 sig figs. My final answer should be rounded to 1.2. This number rounding to 1.2 with 2 sig figs. Now, naturally, looking at this calculation, I don't think I would have known that this should only have 2 sig figs. This has 3. This has 4. this has 3. It's pretty interesting that it comes out to only 2 sig figs in the end, but that's the number of sig figs you should have. So remember, do the calculation without rounding, so you have the number. Then you have to go step by step using the rules to figure out how many sig figs it should have at the end. Now that we know how to figure out how many sig figs a calculated number should have, how do we know which one to round when our uncertainty and our number, if it's a calculated number, do not match? We learned before with measured numbers, the uncertainty is king, okay? And we match the number to the uncertainty. With this, however, it's the other way around. The number is king. And so if we had a number like this, we would, instead of matching the number to the, instead of matching the number to the uncertainty, we match the uncertainty to the number, as shown. So in this one right here, this one should be rounded to like this, right, where we round it up. And so this is our correctly rounded, where the number is king with a calculated number. So now what you need to do in your lab is you need to go through and you need to look at every single number in your lab. And you need to make sure that anytime you have a quantity that was measured or calculated, it has the same precision, right? Or in other words, that means like the last decimal place, has the same precision as the uncertainty, as its corresponding uncertainty. Okay, and with measured numbers, if it's a measured number and they don't match, you've got to round the number to match the uncertainty, right? Because the uncertainty is king with measured numbers. Calculated numbers, you have to first figure out the number of significant figures in that calculated quantity first, using the rules we discussed. And then you round the uncertainty to match the number, because the number is king with calculated quantities. Okay, and then last of all, you need to look at all your sample calculations and make sure that the final answer is with the correct number of significant figures as well. And this is true for all of your numbers throughout your lab, not just in your data tables or your sample calculations, but anytime you even discuss numbers in words, right, you need to make sure that they're listed to the correct number of sig figs.